I'll talk about some fairly recent work on thinking about an old problem, which is the underdoped region of the cuprate superconductors. What happened? Okay. All right, so a fundamental role in everything I'm going to talk about will be played by the Luttinger relation. So this is a very basic relationship in solid-state physics, satisfied by any metal. So if you have a metallic state, the metallic state is characterized by a Fermi surface. This is the surface that separates the occupied and empty states for free electrons. But it's also very well defined for interacting electrons by appropriate singularity in the Green's function. Now, for free electrons, we know that the number of occupied states is constrained by the density of electrons. And a very deep statement of condensed matter physics is that this volume enclosed by the Fermi surface is, in a sense, a topological invariant, that it doesn't change as you turn on interactions between the electrons. But it's also important to realize that this is not an exact statement, as, of course, will be discussed in great detail in my talk, but it's a perturbative statement. It's a statement of continuity, that if you start with a free electron gas and you turn on interactions, and as long as you don't undergo any quantum phase transition, then the volume will remain invariant. That is a correct statement and can be proven. Was proven by Luttinger, and there are also many other proofs since then. Okay, so this talk really is about violation of this Luttinger relations, metals where this relation doesn't hold. And the simplest context where that appears first is in the Kondo lattice model. So the Kondo lattice model is a model of spins coupled to electrons, and it applies very well to many so-called heavy fermion materials, and the class of which has grown a lot. And that turns out to be the simplest context in which we can discuss the violation of the Luttinger relation. But my major focus of the talk is really about the cuprates. And the cuprates are well known to be not described by a Kondo lattice model. They're better described by a Hubbard model, which is a model, just a single band model with no separation between spins and electrons. And the question is really, the key question in my mind and in many other people's mind has been, can you get violations of the Luttinger relation in a single band model? And what are there good ways of describing such phases? So that's really the focus of my talk. But let's just begin in a very simple context. So today we know that electrons at half filling can form spin liquids, which don't have any broken symmetry and have various subtle forms of topological order. Simplest example would be the Z2 spin liquid, or which is a version of Anderson's resonating valence Born state. And so this state is a state of electrons where the density of electrons per unit cell is 1. And if this was a metal, that would mean there has to be a Fermi surface, because that only half fills the band of free electrons. So in some sense, just the existence of a spin liquid is an example, if you wish, of a violation of the Luttinger relation. But you may not like this. You say, well, this is really not a fair example because it's not a metal, it's an insulator. And an insulator, well, maybe Luttinger wasn't thinking about insulators. But now let's imagine we go to a Kondo lattice, where in addition to this insulator that forms a spin liquid, you have a bunch of electrons in a different band, conduction band, the C electrons, of density P. So now, if these are decoupled, these conduction electrons will form a Fermi surface, and the volume enclosed by the Fermi surface would be P, whereas the total density of electrons in this material is 1 plus P. And then this seems to violate the Luttinger relation. This is also a metal. Okay, but there's still, this seems too trivial an example because these systems are not coupled. But what happens if you couple them? And for a long time, it was believed that if you coupled a bunch of spins to conduction electron, you would get a phase where you do obey the Luttinger theorem, where you get a large Fermi surface, the so-called heavy Fermi liquid phase, which I'll say a bit more about in a few minutes. But the point is that, in fact, you need not get that phase. And this trivial situation where the two systems are decoupled can survive for a finite range of JK. You can do perturbative calculations and RG calculations and large N calculations to show that, in fact, this configuration is stable. And you can get a metal now where these two systems are coupled, where there is explicitly a violation of the Luttinger relation. But you paid a price for getting this violation. And the price is that you have this topological order. You have the topological excitations of the spin liquid that are still present in this metal. So that's really ultimately the only way you can violate the Luttinger relation, by having some kind of topological structure, as in this very simple example. Okay, so let's say a bit more about this. So here I write down the Hamiltonian. These are the conduction electrons. These are the spins with the Heisenberg coupling J sub h. And this is the Kondo coupling between the spins and the conduction electron. So when JK is small, you have this FL star state where you violate the Luttinger theorem. And what's a very simple wave function for this state? Well, these two systems are just decoupled. So I'm sorry, I haven't introduced the notation. I represent the spins by the F electrons. So you make a slated determinant of F and a slated determinant of C, and then you project onto one F electron per site. And this would be a simple variational wave function, which is actually just this wave function here. Free electrons on this side, and some kind of projected VCS, projected stated determinant to describe the spin liquid. Okay. On the other hand, what happens at large JK, and that's the famous large Fermi surface state, which is seen in many, many experiments. That's the heavy Fermi liquid state. What happens here is that the two systems mix, and a trial wave function is you make a single slated determinant now of linear combination of the two orbitals. That's what the JK does. And then you just have to remember that the spin, these F electrons are really not free, so you just project onto one F per site. So this would be a very different wave function from this one. This has a large Fermi surface. This one doesn't. And the only subtlety here is, this projection operation. And you need a bit of theory to understand that this projection operation is mild in the sense that it doesn't change the volume of the Fermi surface. But what it does do is make the effective mass of the quasiparticles very large. So that's, but it doesn't change the volume of the Fermi surface. So formally, the way you do this is in terms of a gauge theory. So I should have really written this a bit earlier. You write the spins in terms of the F electrons. And when you do that, because of this local constraint, there's an emergent U1 gauge symmetry. So the Kondo lattice Hamiltonian, when written in this formulation, has a large symmetry. There's the electromagnetic symmetry and then the gauge symmetry. Now what happens in this small Fermi surface state is these two symmetries are really kind of decoupled from each other because the two systems are decoupled. The U1 gauge symmetry does whatever it needs to do to form a spin liquid. And it's only the electrons, the C fermions, that carry the electromagnetic charge. And the Luttinger arguments really can be related to, is deeply connected to this U1 gauge symmetry being present, this gauge U1, global U1 symmetry being present. And so if you just apply the Luttinger argument to this weakly coupled system, you will get a small Fermi surface. On the other hand, if in this language, the tricky part is getting the heavy Fermi liquid phase, which has the conventional Fermi surface volume. So what happens there? Well, the way you think about it is that what happens, since what we've noticed in this wave function is that the F and the C are getting hybridized. In the gauge theory language, this is equivalent to saying that there's a Higgs boson, B, which is this kind of bound state of F and C, or an exciton, which is condensed. Now, if you look at this boson B, it has both U1 gauge charge, because it has an F here, And it also has an EM charge because it has a C here. So this gauge boson transforms under both of these charges. So when it condenses, what it breaks is the, well, which one? I guess the sum of the charges and leaves the other one invariant. No, it breaks the difference of the charges and leaves the sum invariant. So what's another way to say this is that this condensation of the boson breaks the U1 cross U1 symmetry to an unbroken diagonal symmetry, where both F and C have the same charge. So now when you apply the Luttinger theorem has to be applied to unbroken U1 symmetries, and you apply it to the unbroken diagonal symmetry, you get a large Fermi surface. Of course, this is the world's most complicated way of describing the large Fermi liquid state. You could start from the zero interaction limit and just turn on interactions, you will get the large Fermi surface state. But if you start from this infinite interaction limit of the Kondo lattice, you can also get it, but it involves breaking this U1 symmetry in this subtle way. Okay. Finally, let me just mention some recent experiment just came out a few months ago in Science on cerium, cobalt, indium 5. These are experiments involving both photoemission, Hall effect measurements and quantum oscillation measurements of the Fermi surface size as a function of, I think, doping. What is it? Doped electrons. I think they're changing the concentration of cobalt, if I remember. And they see very clearly this kind of phase transition that's postulated here between a small Fermi surface and a large Fermi surface phase without any broken symmetry in either of the two phases. Okay, so that's meant to be just kind of like a warm-up of the Kondo lattice model and the Luttinger relation and the different ways it can be realized in one phase where the spins are decoupled from the conduction electrons. That's the FL star phase, and the other phase where they're part of the conduction Fermi C, and so you get a large Fermi surface. And both are allowed possibilities. Theoretically, you can establish the stability of both with very little doubt, and it's nice that also in experiments, now there's indications of both being observed. All right. Maybe, so if there's any question on that, this would be a time, because now I'm going to turn to the central focus, which is the cuprates, which is a much more complicated game, even though the system microscopically is much simpler. Yeah, Leah.
Can you show that it's, there's no confinement, there's no...
well, okay, so...
FL star is stable?
Yeah, so Leo's question was, what about the gauge field? So so there is a U1 gauge field associated with the U1 gauge, but not with U1 EM. We ignore that. That's the electromagnetic gauge field. That's very weakly coupled. But the U1 gauge is very strongly coupled. Now, in the HFL phase, that's Higgs because you have a Higgs boson that condenses. So basically, you don't have to worry about it. It's just some kind of Fermi liquid-like renormalization. In the FL star phase, it's present, and that just determines the structure of the U1 of the spin liquid. So whatever is happening here, this resonance here is described by that gauge field. And of course, there's many possible fates. It could be broken down to Z2 to get a Z2 spin liquid, or you could have a spin-on Fermi surface. There's a huge... Right, so you would, there's the whole library of spin liquid phases is open to you that many people in this collaboration have worked. I think tomorrow we'll hear more about latest on the classification of such spin liquids. And all of that will just transfer here with almost no change. I'm not sure I know what is a variety, excuse me. The Fermi, let me say it in my pedestrian terms. So the simplest term for free non-interacting electrons, you have some function E of k. So k is a vector, kx and ky, and it's periodic because you're living in a Brillouin zone. So it's a function of, E of k is a function on a torus. And the Fermi surface is the zero of this E of k. It's a real function, and this is the zero. So that's the way you define it. Sorry? It can be anything. It's a periodic function on it's a function on a torus. It could be any smooth function on a torus. Then that's for non-interacting electrons. If you want to describe interacting electrons, then you have to look at the Green's function at zero frequency, the inverse of the Green's function at zero frequency. And that has a zero again. So that's a more complex, analytic functions. But if you look at the zero frequency component of it, it has a zero. So again, it's just some equation for the zero of the Green's function. Yeah.
You see me, please?
I mean, if the U1 EM is broken to discrete, like a Z4 or subgroup, is there a descendant version of the Luttinger relation?
Yeah, so no, the short answer is no. I mean, the Luttinger relation is related to a global symmetry. So there's a global U, every time there's a global U1 symmetry, then there's a Luttinger relation associated with the charge of total charge of that global U1 symmetry. So that when I'm calling density of electrons, what I really mean is the total charge of the global U1 symmetry. So every time there's a global, unbroken global U1 symmetry, it could be charge or spin or anything else, there is a Luttinger relation for every unbroken global U1 symmetry in any quantum system. Right. So, but if you break it, like in a superconductor, there is no, or in a Bose condensate, superfluid, then there is no global U1, then there is no Luttinger relation. So, so you just always have to look for unbroken U1s to get Luttinger relation. So what happens here, for example, in the FL star phase, in the simplest scenario is that both U1s are unbroken. Then there'll be two Luttinger relations. One constraining the size of the spin-on Fermi surface, the other constraining the size of the electron Fermi surface. Now, what could happen is the gauge U1 could be broken onto Z2. You get a Z2 spin liquid, and then there is no Luttinger constraint, at least on the Fermi surface. There could be other anomalies of the Z2 spin liquid that you could worry about, but there's no Luttinger constraint on any Fermi surface of the Z2 spin liquid. But there is still a Luttinger constraint on the conduction electron Fermi surface. When you Higgs them diagonally, there's only one unbroken global U1 symmetry, which is U1 diag. And that gives you the usual Luttinger relation. All right, great. So now let's go to the cuprates. So this is just a single band Hubbard model. Nothing could be simpler. Just electrons with some dispersion EP and some local interaction U. And we are interested in the large U limit at some generic density. So the Luttinger theorem would say, okay, here we measure P. This is just convention. P is the density away from half filling. So we have 1 plus P holes, or 1 minus P electrons. And so there should be a Fermi surface of this volume. This is what we call the large Fermi surface. So we have these, let's think in terms of holes. So you have 1 plus P holes moving in this Hubbard model. Okay, so what's called the vanilla theory would be say, okay, yes, Luttinger theorem applies, and you should do exactly what we did for the heavy fermion state. You just make a Slater determinant free fermion wave function. But here, because you have a large U, you just project out all W occupied sites. And that will give you a large Fermi surface. And the only effect of the projection would be the so-called Brinkman-Rice enhancement of the quasi-particle mass as P goes to 0, and M star over M goes as 1 over P. So, this is the so-called vanilla theory as labeled in this famous paper by many famous people. And this theory certainly is very successful, but at large P. So here's our phase diagram as a function of P. you have an insulator at half filling, and at very large P, you have the Fermi liquid phase. And here's one of many experiments. Here's the photo emission experiment, measuring the Fermi surface by photo emission. And if you integrate the area of this region here, you will get an area in appropriate units of 1 plus P. And that's very well verified in many experiments. For P above, let's say 0.25 or something in the overdope regime. However, of course, I wouldn't be here talking about this, as I'm sure many of you know. This kind of relation seems to break badly at low doping. And the rest of my talk is really about the pseudogap metal phase that appears closer to the insulator. Now, I should say, of course, my focus here also will be at somewhat higher temperatures, let's say 100 Kelvin and above, where there's a metallic phase and no experimental indication of any real broken symmetry. There's a whole wealth of broken symmetries and all kinds of subtleties that happen at lower temperatures, which I'll have nothing to say about. As we'll see, the pseudogap metal phase, I'm going to describe it as a zero temperature quantum phase, which in principle in some universe could be stable even at zero temperature. But in the real world, it probably isn't. And it probably undergoes some kind of confinement transition. But that's not a question I'll talk about. That's certainly an interesting question, and many papers have been written on it. But let's just see if we can understand this higher temperature regime on its own terms. So one point of view is you start with a low temperature phase and find all kinds of broken symmetries, and then you make some fluctuating theory of them. That's not what I'm going to do. I'm going to assume that you should really think about this on its own terms as a quantum phase in its own right. And I think that's reasonable because these temperatures, even though they're relatively high, are much smaller than the exchange coupling, which is 1600 Kelvin. Okay. All right, so if you do photo emission of exactly the type I just showed you, you get these famous Fermi arc spectrum. This is at zero energy, some very high intensity along these arcs. And this is extremely immediately mysterious because there's no such thing as an arc in anybody's theory. At least, Fermi surfaces have to be closed curves. So what's going on? And there seems to be no intensity at zero energy in this region of the Brillouin zone, which is called the antinodal region. So if you look more carefully in the antinodal region, you get rather complicated behavior. So this is in this compound Vi2201. If you're at higher temperatures, you see this red line, that's the dispersion. So this direction Ky is the dispersion along this axis here. If you go along this way, then you see this dispersion of the red line. And notice this crosses zero. So this point here and this point here are the Fermi wave vectors. And those correspond to these points here. This point over there and this point over there. So if you look at the dispersion along this direction, you'll get a zero crossing in the overdope side or at higher temperatures. And that's what you see. Oops. And that's what you see over here. But when you lower the temperature, ignore the green line, you get this blue line. You get this fully gapped spectrum. You can only see the excitations below the Fermi level in photo emission, just by the nature of the experiment. And so this is separated from zero, so that's like a gap. This is the kind of spectrum you might expect in a superconductor, but I don't think anybody believes this is really due to superconducting fluctuations at these temperatures. On the other hand, if you looked in the nodal region, that is, if you went this way through the arc region, then you see hardly any difference between the overdoped and the underdoped side in the red and blue lines that's shown over here. They both have a Fermi crossing at appropriate values of momentum. Okay. So that's photo emission. So here's another recent experiment by the group of Brad Ramshaw, Nature Physics in Press. This measures angle-dependent magnetoresistance. And again, I won't go through the details of it, but which is also a way of measuring the Fermi surface with some analysis. And the big difference between this measurement and the photoemission measurement is that in this measurement, you don't take an electron out of the sample. So it's just measuring the quasi-particles as they're moving in the magnetic field. If they're there, you'll see them. On the other hand, when you take an electron out of the sample in photoemission, there is an amplitude factor, and that amplitude factor is the overlap between a bare electron and the renormalized electron. So that factor can be highly momentum dependent. So one scenario, which is the one I'm going to investigate really, is that these arcs are really portions of a full Fermi surface, of ellipse of some type, and the backside has very low intensity because of this overlap factor being very small. Okay. But that's not something that influences ADMR, angle-dependent magnetoresistance. So what they find, just to summarize this rather complicated but beautiful data, that in the overdoped side, everything works beautifully with this kind of Fermi surface, just as you see in photoemission. But on the underdoped side, what works is something that's similar to this kind of Fermi surface here, where I'm showing now where they postulate both the front and the back side. Okay, all right, so that's two of many hundreds of experiments, some of the latest ones, all indicating that there's something like FL star. I mean, that's certainly a starting point for understanding what's going on, that you have these small pockets in some metallic state with a Fermi surface of size p, because it's not the big Fermi surface of size 1 plus p, but of size p. And the analogy with the Kondo lattice, this would be very natural, where you had in one phase, FL phase, the spins were part of the Fermi sea, in the others they weren't. The only trouble is here, there is no natural distinction between spins and electrons. Everything is the same. So how do you get an FL star phase? Yes?
So in the Kondo lattice there, you were tuning the Kondo coupling.
Yes.
Is there a transition there as a function? There's no transition as a function of doping, is there?
Well, in fact, the experiment was as a function of doping.
It was,
theory,
okay.
you were, yes.
But in the theory, do you have a transition as a function if you fix?
I mean, you can.
You can?
Imagine, yeah. I haven't, you'd have to do a microscopic calculation, but I don't see any reason why you shouldn't be able to see it even as a function of doping. Theoretically, it's much easier to think in terms of tuning JK. Here, we are tuning doping. I will introduce something like a JK very shortly. as a
In the model, in the Kondo model, you can tune chemical potential. So what happens?
Your seat mic, please.
What happens there? Function of chemical potential.
Well, I fixed JK, yeah, it's hard to say. I mean, I think that'll depend on geometry of the Fermi surface and many details, yeah. I guess you could say when the conduction electrons are very small, density small, they should be in an FL star. When they're higher, it's more likely to be in FL, but that's a guess, yeah. Okay, so there's no shortage of theory papers on writing the pseudogap metal as something like FL star. I put an approximately equal because people call it many different things. Probably the original idea is in the paper by Wen and Lee, going back a long time. And there's also papers by me and my collaborators. But I'm not going to talk about any of those because, well, the general idea is basically correct, I believe. It leaves a lot to be desired because it doesn't give you any way of actually computing something we can compare with experiments. But what I want to present today is a new set of ideas, which really try to draw what I claim should be the right lesson from the Kondo lattice. And the right lesson is you don't fractionalize the electron. So this kind of ansatz, we take an electron and write it as a product of a fermion that carries a spin and a boson that carries the charge, or the other way around, is really the foundation of all the papers that I just mentioned. So you assume some kind of spin charge separation, and then you try to build some theory of a metallic state. Now, this runs into trouble because what you see in the experiments is not a spin-on or a hole-on. You see an electron. So the proposal is that there are some interactions that lead to fractionalization, but then some fraction of the charge carriers rebind to form an electron again. And just that rebinding process is very complicated to implement, and which is why all these theories that I mentioned, including many by myself, have run into all kinds of trouble. And this rebinding quite easily has to occur in a model where this hopping scale T is much larger than the exchange scale J, because the fractionalization is preferred by exchange scale J, whereas the hopping T, you can easily see, is just an attractive interaction between the F and the V. So some of the dopant electrons want to rebind, and just doing this two-stage process seems awful. So just don't do it. So what do you do? Okay, so this I'll present a new way of doing it. The original idea is due to Yahui Zhang, who's a postdoc at Harvard and is now a faculty member at Johns Hopkins as of a few weeks ago, and also worked by my students, Alexander Nikolenko and Maria Tikhonovskaya, and also recently we had a collaboration with Eric Mascott and his advisor, Dirk Moore at University of Chicago. All right, so we start with the Hubbard model. This is the original model. And then here's an exact identity, replacing the Hubbard interaction by something to depend on the spin squared. And then you take the spin squared and you decouple it by a Hubbard-Trutanovich transformation. So you introduce a boson phi, which I'll call a rotor, for reasons become clear in a minute. So the three-component boson, which is coupled linearly by this Yukawa-type coupling to the electrons. So this is an exact representation of the Hubbard model, which is the foundation of the Hertz-Millis theory of antiferromagnetism and the Paramagnon theory, really, of going back to Scalapino and others, Burke and Schrieffer. It's been everywhere. It's the theory of spin fluctuations in a metal, and phi is some kind of collective mode that represents the spin fluctuations. Okay, so I want to take the same starting point. Now, if you just take this theory as written down and do all kinds of perturbative analysis in this Yukawa coupling, then you will get the ordered, magnetically ordered phases. You'll get phase transitions between them, as described by the Hertz-Millis theory and various corrections. But that's not what I want to do, because that isn't compatible with the kind of phenomenology I've been talking about. So what are we going to do? So here's the two steps. First of all, I want to write it in a Hamiltonian form. So I'll take this phi field, first of all, just for convenience, restricted to have unit length. So you can think of phi as a field that's valued on the sphere. So on every site of the original lattice, I have a particle, a fictitious blue particle here, moving on a sphere, on some fictitious sphere. And the coordinate of that blue particle is phi. So that's coupled to the conduction electrons. And then I imagine, just after some renormalization, I want to give this particle to have some kinetic energy. So the kinetic energy of a particle on a sphere is just its angular momentum squared. And L and phi have the usual commutation relations of a particle moving on a sphere, of angular momentum and its coordinates. Yes?
On the sphere,
Yeah.
I guess I'm wondering, if you were to integrate out phi again, would you recover the initial theory?
Yes.
Okay, so you don't have to allow it to have different magnitudes.
Yeah, I mean, you don't even need to restrict it on a sphere. It's just a question of convenience.
Okay.
Yeah.
Okay.
As you'll see, I'm going to make further approximations. So let me make the next approximation. I'll tell you what I really need.
Okay, thank you.
That's just right here. So if I now look at this this Hamiltonian, just this G over 2L squared, it has eigenvalues G into L plus 1, degeneracy 2L plus 1, L equals 0, 1, 2. That's just the usual angular momenta. So you get a whole bunch of states. So what I'm going to do is I'm going to say, well, just pick the lowest two states, L equals 0 and L equals 1. So that's really what I want. You could take you could take a more general model where phi is not restricted to be of unit length and solve it. But as long as the phi potential is kind of non-monotonic, you will find that the lowest state is L equals 0 and the first state is L equals 1. That's all I want. Okay, I'm just going to pick these two states. And the key step is I'm going to represent these two states, L equals 0 and the L equals 1 state, as the states of two spin a half with an antiferromagnetic coupling. So I have two spin a half, they can form a singlet, they form a triplet. So in the operator language, this is roughly this mapping. The angular momentum is the sum of the two spin a halves, and phi is the difference of the two spin a halves. Notice there's a difference in sign here. So there's no symmetry there's no reflection symmetry between 1 and 2. One of them is ferromagnetically coupled, the other is antiferromagnetically coupled, and that's important. Okay, so then I can replace this model, which is so far essentially an exact representation of the Hubbard model, by this model right here. I replace each rotor by two spin a halves with a coupling J perp between them. And now I'm going to just call this a Kondo coupling, because it's a coupling between electrons and spins. And this is my Hamiltonian, where I have two layers of spins with a coupling J perp between them, and an antiferromagnetic Kondo coupling between the first layer and the electrons. There's also coupling between the electron and the second layer, but let me just ignore it for simplicity. And this is my Hamiltonian. I've also added couplings in this direction. Okay. All right, so now I can do what you suggested. Let's go backwards. And now let's take the limit of large J perp. So in large J perp, these two would form a singlet. And then you just canonically get rid of these states by a canonical transformation, or sometimes called the Schiefer-Wolff transformation. And you do that, and you get back the original Hubbard model with some additional exchange interactions, but that's it. So formally, depending on how hard you're willing to work, and perturbation theory in J perp and various other couplings, this is an exact rewriting of the single band Hubbard model. Okay. So the important point here is that other people have talked about adding new degrees of freedom before, but the important point is you can only add not one layer but two layers. Two layers of spins are trivial in every way. They have a trivial ground state, which is spins form a singlet. If you add one layer, it does not have a trivial ground state. That will change the physics completely. But you can add two. And this is just a rewriting of the Hubbard model. Yeah?
Can you comment on the different coupling to S1 and S2? How do you see that?
Use your seat mic, please.
Can you say different coupling to S1 and S2?
Right, so if phi is S1 S2 minus S1.
Or you couple to phi.
Yeah, so you couple to phi here. So what you notice here is that S1 has an antiferromagnetic Kondo coupling, whereas S2 has a ferromagnetic Kondo coupling.
I see. And then
we believe ferromagnetic coupling comes in not important, so I just remove it.
I see. Thank you.
All right. In fact, this is the way we originally did it. The Paramagnon way is a nice way to think about it, and it connects to many other previous works. The number of papers of electrons coupled to Paramagnon is approaching infinity. All we're doing is taking the Paramagnon and splitting into two. All right. So what does that give you? Well, first of all, now I have my JK, but I'm going to vary, not doping, so with Leo's permission. So when JK is small, then these spins will form singlets. And you can integrate them out, and you just they form a trivial insulator, and you get the large Fermi surface here. Okay, so that's nothing new. That's the Fermi liquid phase. But now I can get very easily an FL star phase. What do? I take the top 2 layers and make them do what a Kondo lattice does. So now I assume this JK is large. So these conduction electrons would form a large Fermi surface with the first layer of spins. What is the density of electrons or holes here? We have density 1 plus p here. You have density 1 here. So the total density is 2 plus p. And remember, because we are on a torus, the volume of the Fermi surface is modulo 2. And so that's the same as p. So that's actually a small Fermi surface. So with these densities, the large Fermi surface of the Kondo lattice models becomes the small Fermi surface of the conduction electrons of the Hubbard model. And then, however, you still have the second layer left here. And these, well, they're there, and they'll form a spin liquid. So, there'll be a spin liquid of the second layer, and it has to be there. And the reason it has to be there is because the top 2 layers form a metal, and those layers, the top 2 layers, violate the Luttinger theorem for the original Hubbard model. Of course, they're obeying the Luttinger theorem for the top 2 layers, but they're violating the Luttinger theorem for the original Hubbard model. And the only way you can violate the Luttinger relation is by having some topological excitations. What this does is put all of those topological excitations in the bottom layer. So technically, this turns out to be a very useful simplification because it separates, as in the Kondo lattice, the topological physics of the spin liquid from the metallic physics of the Fermi liquid. They reside in different regions, and that allows you to really do calculations very easily. Okay. Okay, how am I doing on time? Oh, not too bad. All right, so there's a way to write down a gauge theory. It's a bit more complicated here. Previously, I had only a U1 gauge theory. Here, if you do the most general case, you get a gauge group which is SU2 cross SU2 cross SU2 slash Z2. But no worries, most of the gauge symmetries are broken. Roughly speaking, where does this come from? Well, you have two layers, the psi1 layer and the psi2 layer. And these have a constraint, local constraint, because they're spins. And the most general way to describe that is in terms of an SU2 gauge theory. So you can read this Reviews of Modern Physics of Lee and Nagosa. We just apply exactly that to both layers. And in this kind of matrix notation, these two SU2s correspond to a right multiplication of the SU2 on this 2 by 2 matrix. On the other hand, there's another constraint. In the end, you want these spins to form singlets. You want to get rid of the triplet degrees of freedom here. And the way you can do that is by putting this softer constraint, S1 plus S2 equals approximately 0. And that you obtain by left multiplication. So that's where you get and you have to take the same U here because you want the sum of the spins to go to 0, not the individual spins. Anyway, so you can do all kinds of fancy gauge theories, which lead to strongly coupled problems. But in this phase, fortunately, in this phase, the interesting phase with the small Fermi surface, essentially everything is broken. All of the first two SU2s are totally broken by a Higgs field, the same Higgs field that led to the large Fermi surface in the Kondo lattice. And there's only one SU2 left over, which is on this final layer. But that's an insulator, so let me ignore that for now. So if I just look at the first 2 layers, I get a very simple theory. You have the C electrons in the top layer. You have the psi1 layer with some hopping T1. And this is really the only adjustable parameter here. And then you have the Higgs field that hybridizes the top layer to the middle layer, which we call phi. All right, so phi basically determines the pseudogap, and you can compare to experiments. So you just figure out what these T1s are. These T you know from experiments, and then you try to fit the data. So for example, here, this is the theory. I believe the red line is the Fermi surface of the C on their own. The black dashed line is the Fermi surface of the T1. And phi hybridizes them, and this is the blue line is the Fermi surface you get. And if you put in the intensities, you get these arc-like features with very weak intensity at the back, this very simple mean field theory. But more interestingly, so that's this feature here, let's look at what happens when you go over here. And you can, very simply reproduce all the features that are seen. So here again, the red line and the blue line are the dispersions of the C and the psi, and the red line and the black line. The blue line is the actual electron spectrum. This is at the antinode. This is at the node. And now you can compare the intensities here with the experiments, which are on the bottom line. And we can, with not too much playing around, really very easily fit all the general features of the observations. One important feature that in particular Patrick Lee has emphasized is that this Fermi wave vector here of the overdoped side, or at higher temperatures, does not coincide with the maximum of the dispersion. And use that to argue that there must be a pair density wave. But the same feature is easily reproduced by this theory. It just comes from the fact that the Fermi surface crossing of the black line is different from the Fermi surface crossing of the red line. Their densities are different. One is at density 1, the other is at density 1 minus p, and so on. Anyway, so that seems to work very well. All right, so that's a simple model of just the simplest mean field theory on this theory obtained by fractionalizing the Paramagnon. So now that's to 60 minutes, that's 3 minutes, right? Is that right? Okay. So finally, let me just say a few things. It'll correct to work by others in this collaboration. What about the spin liquid? So at this point, I haven't said anything about it. The theory is compatible to any choice you might make. And this spin liquid does have experimental consequences. If you actually measured spin correlation functions in a neutron scattering, you should see these excitations. And in photoemission, it will come in normalizing the self-energy of the electron. So the electron in the top two layers will couple with the spin excitations in the bottom layer. And we can also, we're just going to treat that perturbatively in these couplings here. But the point here is that all the singular gauge stuff that you have to worry about, it's all in this layer. And we know a lot now today of how to treat singular gauge fluctuations as spin liquids, insulating spin liquids. We can just use all of that. So what's a natural spin liquid for this third layer? Well, one possibility is to take the studies of the J1, J2 antiferromagnet. Let's take the spin-a-half antiferromagnet on the square lattice with first and second neighbor couplings. Again, there's a huge amount of work on this problem with a lot of controversy and a very large number of interesting theoretical ideas and beautiful numerical analysis. Just in the last 2 years or so, there seems to be emerging a consensus. So given my long history in this field, I feel very happy. Finally, everyone's agreeing, so at least the numerical people. And the consensus seems to be that as you turn up the second neighbor exchange, you go from a Néel state via an intermediate spin liquid, which is gapless, to the valence bond solid. In fact, this was first identified in this paper by Federico Becca and others. So they may have had a specific ansatz for this spin liquid. In particular, the ansatz they proposed was the spin liquid in Wenn's classification, Z2A, ZZ13. So we've been studying this spin liquid and looking at its phase transitions from this spin liquid, possible phase transition to the Néel state or the valence bond solid state. And one attractive scenario is that the famous pi flux state is possibly unstable to the Néel state, and the staggered flux state is unstable to valence bond solid. And actually, what you're seeing is this evolution from the pi flux phase to this gapless Z2 spin liquid. So this blue line here is our proposal for what happens as you go increase J2 along this direction. Okay, so we've, in this paper with Henry Shackleton and Alex Thompson, we've tried to work out a theory of how you go from the pi flux phase to this gapless Z2 spin liquid. And this is what it looks like. So this is the theory, well-known theory of the pi flux phase that Mike Hermele and Xiaogang have written many papers on. Two flavors of Dirac fermions coupled to an SU2 gauge field. But to get a Z2 spin liquid, you need a Higgs field to break SU2 down to Z2. So turn out you need two vector Higgs fields, phi1 and phi2. And when you condense them with proper symmetry signature, you will get this gapless Z2 spin liquid. Okay, so I just want, the reason I'm going through this and mention here, this particular theory has some emergent subsystem symmetries, which leads to all kinds of anomalies and possibly connected to a lot of work being done on emergent subsystem symmetries by others in this collaboration. Let me just finish. So the last slide is you can also take this spin liquid and compute the spectrum of the electrons. And this is something in the latest paper where we compute the spectrum of the electrons, a function of frequency and momentum. And it does reasonably well when compared to photo emission spectra. Okay, let me just end there. All right, thank you.
If there's any more questions?
Yes, thanks for the very nice talk. I was wondering, there's two things I noticed that lead to a question, which is that it seems like there's sort of a general idea that you have going, which is that you're recombining all these degrees of freedom, and then what you find is that there's sort of a metal, some sort of emergent metal within that, and that breaks this Luttinger relation. That's the first fact. Second one is that, of course, Luttinger relation, I would think, is, some equality. So in a sense, it's sort of like the space of things that could happen at sort of measure zero. So.
Sorry, I missed the second part.
Yeah. So we find that there can be a violation of this relation. And so sort of the space of ways to violate it is much larger than the space of ways to not violate it, it seems, just because it's an equality, just heuristically. So I guess why isn't this more common is what I'm wondering. Or are there large spaces where this is violated? Yeah.
Right. So I think the way to say this is in any many-body quantum system, which has any global U1 symmetry, there is a Luttinger relation, which is unbroken. I mean, that's period. The usual familiar Luttinger relation is just the simplest realization of that. But if in these other phases we're talking about, once you allow for topological phases, the way the symmetry acts on the various excitations can become quite complicated, and you get new extended Luttinger relations. So these phases that we're discussing, the FL star phase, has a constraint of its own. It's not, it's the volume of the small Fermi surface is constrained to be P. It can't be anything else, at least in this simple setup. There can be more complicated setup. Yeah, so once you realize that there's different ways of combining topological order with the global symmetry and getting new Luttinger relations, I agree, the possibilities seem endless. But it's not as if the Luttinger relation disappears. So another version of this relation, even in a spin liquid, like the Z2 spin liquid that I mentioned at the very beginning of my talk, that has integer density of electrons. I said there's no Fermi surface. So what is the consequence of the fact it's exactly integer density? Well, the consequence of the fact is that the Z2 spin liquid has to be what's called odd. That is, you have these flux excitations, and these flux excitations, the visons, they must move in a pi flux background. That's a Luttinger relation also. Okay, so there's some remnant of it everywhere. And this whole theory of symmetry-enriched topological phases is, in some sense, the new modern version of Luttinger relations.
Let me read a question which has been asked online. What is the nature of the transition between the FL and FL star phases?
Ah, wonderful. Okay. So that it actually depends. So the answer for the Kondo lattice is it's a U1, the simplest case. It would be just a U1 gauge theory where you have a critical Higgs field and you have a Fermi surface. So you have to do a theory of bosons and fermions coupled to of U1 gauge theory. Okay, it's still a strongly coupled theory, but we are understanding more things about it. For this transition for a single band model, the theory turns out to be quite different. And the simplest case is you don't just get a U1 theory, you get an SU2 cross U1 theory. And that's again coupled to the Higgs boson, but also the large Fermi surface of the electrons. And then there's also these these layers, the extra layers that I added, actually come back to life. They had become deconfined excitations. And so there's a prediction here that there's an extra ghost Fermi surface of the second layer right at the critical point. And with a lot of caution, then I can show you this slide. If you look at the specific heat between these two cases, so in cerium cobalt indium 5, the specific heat has no singularity near the critical point, whereas the Hall effect jumps, indicating the change in the size of the Fermi surface. In the cuprates, you see the same jump in the Hall effect, but you see huge peak in the specific heat. And anyway, at least the sign of the prediction is correct. Well, we would predict that in the single band model, the specific heat is larger than in the two band model. All right, and there's some indication of that in this experiment.
There's another question asked online. How to describe the strange metal?
That's another talk. Okay, but yeah, the starting point would be this theory right here. Yeah.
But I'm trying to connect it to what's, numerous papers have been written on the subject. So, starting with Hertz-Millis and Chubukov. So, so they have like a Lagrangian description where, you have this Hubbard field phi and you, have maybe some Berry phase term that encodes its precession. Well, actually.
No, they don't have a Berry phase. That's the point.
Well, okay,
There's
so.
no Berry phase there. There's a damping term. But
Well, there's a damping term because it's
we have the
paramagnetic.
damping term too, but
Right.
the damping term comes from right near the Fermi surface.
Right.
So I'm not going to integrate out those electrons.
Right. So I guess my question is this: do you have at a technical level within that approach, where you describe things in terms of these paramagnetic antiferromagnetic fluctuations phi, which are gapped?
Yeah.
What do you technically do, at the Lagrangian level to encode this reduction of the to these 2-qubit description? Like, what do you?
Yeah, it's a good question. So first of all, let me say that this is the Hertz-Millis theory. This is the theory.
Yeah, it's just a Hamiltonian description.
Yeah, just written as a Hamiltonian form.
Yeah.
You can think of this L squared as a d phi d tau squared term.
Yeah.
Which you then throw out in the end because it's much less important than the damping on the Fermi surface.
Yeah.
But there's no Berry phase. All of the Berry phases here are in the electrons, which you haven't integrated out. It doesn't. All right. So what do you have to do? Well, you could just make this decomposition. You could just write phi as S1 minus S2. But now then you do have to write down the Berry phase of the two spins.
Right.
You have to write them down, and you put this phi, and then you have to, this will give you some coupling. I mean, essentially you will get the Hamiltonian, the path integral version of this Hamiltonian, pretty much. Mm-hmm. Okay. Mm-hmm. Okay. Now, but the path integral, that's not so easy to work with because the Berry phase of the spin is a complicated object. Right. So if you go to the Hamiltonian language, it's very easy. You can just do the Schrieffer-Wolff transformation. Yeah. So you do have to treat the spin commutation relations of these two constituent spins in a sense exactly. I mean, that's also even I could say the similar thing about the Kondo effect. Suppose I just take the old Kondo effect. I can write on a path integral for the Kondo effect with the Berry phase with the spin and it coupled to the environment. Mm-hmm. But that's not a very useful way to do it because you have to take the Berry phase of the spin exactly. Mm-hmm. Mm-hmm. And you can do that in some kind of perturbation theory, but you can. Right. But there it's perturbative in J. Here we want to go to large J and so on. It's more like the two impurity Kondo problem. You have two of them in a lattice, and they can form a singlet or a triplet. That's kind of what happens in the two impurity Kondo problem too. Yeah, you can certainly write down a path integral, but it's very important in that consideration to teach the spin Berry phase exactly.
Right. It's because you want spin to be quantized.
Yeah, it's
But,
quantization of
but with the
spin.
Berry phase term is what's encoding that quantization, which is easy in the Hamiltonian, but not Lagrangian.
Yes, and the quantization of spin is also a version of the Luttinger theorem. It's
Yeah.
the same thing. That has to be done very carefully.
Yeah.
There was another question.
Thanks, Shabir. I thought the match between the arcs of the photoemission spectra was really neat. One thing
Thank
that
you.
didn't match, and I'm curious about, is in the photoemission spectra you showed, there's a break in the spectra in the antinodal, around the antinodal points below the Fermi surface. I'm wondering if that has any, right there, if that has any physical consequences.
I think that's some kind of experimental artifact. I don't think there's anything real associated with that. So first of all, these lines here, these are the positions of various peaks. The actual spectrum looks something like this. It's hiding a lot of stuff. So, they're looking at this is the actual spectrum, and they're plotting the position of these peaks in the spectrum. And sometimes, I don't know exactly what's going on, but I trust their analysis. This is this is the highest precision data, and they've done a really careful job over many years. And we do have many free parameters, but I will say that, it is quite, to us, it's very encouraging that it just fits without working very hard. It just fits everything.
One question from Central, which I'd like to read. I suppose Wiedemann Franz will be violated just at this quantum critical point. Current experiments suggest otherwise, but maybe this will change.
Okay, I'll have to think about that, but as usual, I'm sure centralism is right.
Well, so we're kind of out of questions, but maybe one more question. I'm out of time, I meant. But
You should see my please.
Sorry. So in the Kondo case, I imagine like this coupling that you tune is like some physical coupling between the two different degrees of freedom. But in this case where the ancilla qubits are emergent, is there like a microscopic interpretation for what this coupling might correspond to?
Well, if you really want a microscopic relation, we can only make that relation when the coupling J-perp is large and a 1 over J-perp expansion. That we can do. And now you can see the relationship between U and JK and J-perp and so on. So you can do this to any order in J-perp you want. But of course, we don't want to take the large J-perp limit. We want to work at small J-perp. That's when we get our interesting physics. But at that point, sort of solving the whole problem, it's hard to see. One could imagine doing like a matching calculation. Suppose you could, on the computer, numerically solve a single band model and this coupled 3-layer model. You could look at the Fermi surface or the effective mass of the quasi-particles or various other properties, and you can match them to these couplings, which is effectively what we're doing when we're matching to the experiments. But that requires solving a strong coupling problem. But in the limit where J-perp is large, we can do the mapping.